Alright, so in this exercise we're given some strange looking topology and we want to prove that it's Hausdorff but not regular. And the real point of this exercise is the statement that's mentioned in parentheses, which is that so if you look at this topology, it consists of open sets are sets of the form U union V intersect the rationals where U and V are open. So given any open set U which is open in R in the standard topology, meaning the topology of just open intervals, any set which is open in the standard topology is also open in this topology because you just take V to be the empty set, which we know is an open set because it's always an open set. And so that means that this topology that we're given is stronger than the topology, the standard. It's stronger than the standard topology on R, i.e. it has more open sets. But the point is that whereas the standard topology is normal, this one is not. So you can add more open sets to a topology, but lose some of the structure. I.e. here, for example, we lose normality and we even lose regularity because normality implies regularity. But yeah, so let's go about this. So first of all, let's see here. So we need to prove that tau is a topology which is Hausdorff but not regular. So there's actually three things to prove here. First, we have to prove that's a topology. Then we need to prove that's Hausdorff. And then we need to prove that's not regular. Okay. So let's start with proving that it's a topology. And we start with the easy part. So we have the two sets that have to be in there. Empty set in the entire space. And the empty set is in there since we can set U and V to both be the empty set. And R, the entire space, is in this topology since we can set U to be the entire space R and V to be the empty set. Okay, so now we want to prove that this is a topology. So it has these two sets, but it also needs to be closed under arbitrary unions and finite intersections. Alright, so for arbitrary unions, given a collection UI union VI intersected with Q, where I ranges over elements of capital I. So this is going to be a collection which is contained in this topology, so it's a collection of open sets. And furthermore, these indices lowercase I can be let's call this A so that I don't have to differentiate between lowercase and uppercase I. So A can be an arbitrary indexing set here. In particular, it can be uncountable. That's why I'm not doing like I equals 1 to n, because that implies that this must be countable. But that's not enough for unions of sets in topologies. It needs to be closed under arbitrary unions. So unions of sets which can be indexed by arbitrary indexing sets. And so A here, capital A, is just some arbitrary indexing set. Okay, so given this collection, if we take the union over all of these sets, then we just can use set algebra. So we can break this up. We've got the union from overall I and A of UI. Then we take the union with all sets of the form VI intersect Q. But now the Q will distribute here. Is this actually... This certainly should be true, because if you're taking a union of things of the form VI intersect Q, then you should be able to distribute out, or factor out the Q from this. And basically, here's what I want to write this as. So I want to write this as the union over all I and A of UI union, and then we take the union over all I in A of VI intersected with Q. And now these, basically factoring out this intersection with Q here is what I'm doing between these two steps. And just looking at it, I should be able to do it because, let's see here. I guess we could go, well, first of all, you can't use the typical, you can't use the standard rules of set algebra to prove to verify this equality, because the set algebra rules are only for finite things. Like there's rules for how intersections and unions work, and there's the distributivity rule for intersections and unions, which only technically applies to the pairwise case. Like there's A union B intersect C is equal to A union B intersect A union C. This is just a rule about set algebra, but it only holds in this this finite case where we only have one union, and of course this extends to well, actually, it would extend to if you have A union and then B1 intersected through Bn. And this would be A union B1 intersected with all the way through intersected with A union Bn. But this only works for finitely many of Bi's. So in order to prove it for this case where we're actually indexing it by an arbitrary set A. So let's think about this. If you choose any set that's in this union, well, there must be some I such... If you choose any x in the union over all I in A of VI intersect Q, then there must be some I such that this element x is contained in VI intersect Q, which means that it's contained in Q. And since it's contained in VI, it's contained in the union of the VI's, and therefore, the set that we have, this union over all I and A of things of the form VI intersect Q, must be contained in both Q and the union of the VI's, which means that's contained in the intersection of Q with the intersection of the VI, or the union of the VI's. So that's one direction, and for the other direction, if you have some element x which is in the intersection of the rationals with the union of the VI's, then it must be both in the rationals and in one of the VI's. And so it must be in VI intersect Q, which is contained in the thing on the left, and so we have by inclusion. Okay, so yeah, that is as easy as I thought it was. Okay, so this equality holds, and this is in the topology sense union over all I. Let's see here. There's a notation. I want to see if I introduce it here. I guess I don't introduce it in this this exercise. Is that right? Basically, I'm trying to think if I should introduce a... You know what? I'm going to introduce it. So, since union of I of the UI's and the union over all I's of the VI's are open in the standard topology, which we'll call S for standard. Okay, and obviously this is true because each of the UI's is contained in S, and S is closed under arbitrary union, so the union of the UI's is contained in S, and similarly for the union of the VI's. And so we see that this element here that we've come up with, this union of elements in T that we've come up with, is just some element in S union with some element in S intersected with the rationals. And so it's an element in the topology. Okay, so that's unions. For finite intersections, basically for topologies, you only need to prove pairwise intersections, because then finite intersections follows by induction. So as for intersections, if we have U1 union V1 intersected with Q and U2 union with V2 intersected with Q are both elements in T, then we have an ugly computation that proves that the intersection isn't there. It's not too bad, but it's annoying. There might be an easier way to do this, but I did not think of one, and this one was simple enough that I just figured it would be easier for me to just stick with this one than to try to figure out if there's a cleaner way to do this that I'm not thinking of. So we do this intersection, and then we distribute it out using the rules that I mentioned earlier. So what are we going to do? We're going to distribute this intersection. So we're going to take the thing on the left, U1 union V1 intersect with Q, and then we're going to intersect this entire thing with U2. And then we're going to take the union of that with, and now we've got to do the same thing. We again take U1 union V1 intersect Q, and now this time we intersect it with V2 intersected with Q. And then do I have, how many more parentheses do I need? I think just one more. Okay, so we have this. Well, this is equal to, and now we, let's see here, we do another distribution for the first one. So we have U1 intersected with U2. Then we take the union of that with, let's see here, we have V1 intersected with Q intersected with U2. I leave out the extra parentheses because it's just a bunch of intersections, and intersections are associative. Then we take the union of that with, and now we've got U1 intersected with V2 intersected with Q. Union, and now we've got V1 intersected with Q intersected with V2 intersected with Q. I guess I could have reduced that into another step if I wanted to. But anyway, so what do we have now? We have U1 intersected with U2, and we are taking the union with V1 intersect U2 intersect Q, union with U1 intersected with V2 intersected with Q, union with V1 intersected with V2 intersected with Q. And so now this is equal to, we again have U1 intersected with U2, union, and now we have, let's see here, we distribute out the Q, so we get V1 intersected with U2, union, U1 intersected with V2, union, V1 intersected with V2. This entire thing is being intersected with Q. Now we look at this, and we see that U1 intersected with U2, this is just an intersection of open sets in S, and so it itself is an S, because S is closed under finite intersections. And then we look at this other thing, we've got another set here, we've got this union of these three intersections, but everything in here is an open set in S, and so this union of intersections is also going to be in S. And so, therefore, this is exactly the form of an element of T, and so this is an open set. And so, thus, T is a topology, because it has the empty set, it has the entire space R, it's closed under arbitrary unions, and it's closed under pairwise intersections, which implies that it's closed under finite intersections by doing a induction argument, which I'm not going to include here because it's not too like it's something that you can do on your own, and it comes up enough in topology that it doesn't make sense, or it comes up enough in verifying topologies that something is a topology that doesn't make sense to prove it every single time. You can just use it as a fact. Okay, so that's the first thing that we want to prove. Now we want Hausdorffness. Okay. So Guess I didn't need that much room. But T is Hausdorff, since it is stronger than the Hausdorff space S. Or the Hausdorff topology S, I should say. Doesn't really matter. But yeah, so again, like I mentioned before, T is stronger than S because if you let V be the empty set, then any element of S is also in T. So S is a subset of T. So in this scenario, when it comes to Hausdorffness, this is actually preserved under, like, when you add in more sets to a topology. Because what Hausdorffness means is that given any two distinct points, you can find disjoint open neighborhoods of these two distinct points. I.e., given x not equal to y in the space, and there are open sets u and v such that x is in u and y is in v, but u and v do not intersect. And this is true in S because S is Hausdorff, because if you just take the two open, let's see here, so if you just take x not equal to y, you just take like the open interval from x, let's say x is strictly less than y without loss of generality. You let one of the open sets be like the open interval from x minus 1 to the average of x and y, so the midpoint of x and y, which would be x plus y over 2. And then you let the other open interval be from the midpoint x plus y over 2 up to, say, y plus 1. And then you have two disjoint open sets. One contains x and one contains y. And these open intervals are contained in S and thus in T, and so T is Hausdorff. Okay, so Hausdorffness is preserved when you add in more open sets, but we're trying to prove here that normality isn't. So let's move to that. So for regularity, what you need is that, did I say normality beforehand? I always get those two words mixed up, normality and regularity, because in English they mean pretty much the same thing, but in math they mean not the same thing, which is super important. But yeah, so we're proving that these things that this topology is not regular. So regular means that given a closed set and a point not in that closed set, you can sort of find disjoint open covers of these two objects. So you can find so if the closed set is called A and the point is X, then you can find an open cover or an open set U which contains the closed set A and a open set V which contains the point X such that U and V do not intersect. So all we really need here is we want to find a closed set that once you cover it, you'll end up with things that you can't. You basically want to show that, like, you can. Well, actually, no. Instead of me trying to give the intuition, I think I'm just going to end up babbling a lot. Let's just get into the example. So we're actually just going to find one set that sort of makes regularity break. So what we're going to do is let A be all the irrational numbers. Q is open in tau. And why is Q open in tau? Well, you let U be the empty set and V be the entire space R. And so then this element is so this is an element of the form U union V intersect the rationals. So then if you let U equal the empty set and V be all of R, then the set that you end up with is just all the rationals. So the set of rational numbers is open in T. So A is closed because it's a complement of an open set. All right. So let V be an open set such that A is contained in V. Then V equals U prime union V prime intersected with Q. Well, basically, you can sort of think what you're going like. What could an open cover of the irrationals possibly look like? So V equals U prime. This, where these are open sets in the standard topology. And so let's see here. So V is going to contain, if V prime is non-empty, well, if V prime is an open set in the standard topology, if V prime is a non-empty open set in the standard topology, then it's going to contain some rational numbers. So let's see here. A is contained in V. Here, let's write this way. Given any element A in A, so A is an irrational number, A cannot be in V prime intersected with Q, because V prime intersected with Q only contains irrational numbers, if it contains anything. So it cannot contain an irrational number. So A must be in U prime. Thus, V itself is a subset of U prime. Now the only open set in S containing all, here I've got to scroll down a little bit, containing all irrational numbers is the entire space, because the irrationals are dense in R. So let's see here. So A is in U. So V is contained. No. So V equals U prime. So thus, U prime equals R. And in fact, V is equal to U prime, so V is R. Okay, so the only open cover of the closed set A is the entire real line. So then, in fact, for any x in A, well, for any x not in A, and any neighborhood U of x, this is of course a neighborhood in T, U intersect V is non-empty. Well, in fact, U intersect V is going to be equal to U because V is the entire space, and V is not empty because it's an open neighborhood. Thus, T is not regular because there's no way to choose, because given any point not in A, there's no way to find an open cover which is distinct from the open cover of A, because the only open cover of A is the entire space. And so yeah, this proves that the space is not regular, and that's what we want to prove, and so this completes the exercise.